Hi, welcome back. So we are in Chapter 6, Prediction by RCC, and the outline Prediction by Classification to discuss the last outline of this chapter, and that is deep learning. In principle, the idea of deep learning, it shouldn't be as complex as actually it appears to be from at least mathematical background. However, the complexity of the framework, it's really make it a little bit deep in the learning perspective. I have chosen to explore the actually framework of deep learning using a classification. However, the same concept is applicable also for regression problems. So we're looking at this input space, right? Try to help me predict the label of this Y. I'm going to select two features just to easily later on graph that. I have like X1 and X2 features. And for simplicity again, let's consider Y to be a binary label, either 0, 1, 1 minus 1, whatsoever. We have seen this problem from the very beginning using different algorithms, all of which are actually possible to solve a problem. But I would like to approach the problem from different perspectives. We have seen the linear combination of our famous equation that we all know and love, the alpha 0 plus alpha 1 x1 plus alpha 2 x2, etc. So I'm going to use this to make something new. I'm going to take this alpha transpose x plus some alpha naught, which is going to be a value, and I'm going to fix this into another function. So the outcome, which is this guy, the scalar function called a step function. I think we discussed step function before. Larger than 0, then it is 1. Otherwise, it is going to be 0. So let's call this a step function to be 1 if this outcome, which is this guy here, larger than or equal to 0. And let's call this phi 1. It's fine. If I want to graph this outcome of this, it could be in the 1 region here or the 0 region here. So this is one phi. I can do it one more time. Let's take another phi. And I keep doing that. But you say, what's the purpose? Well, I want you to observe, first of all, I was relying on a constant value of x1 and x2. Always there, the input space. I mean, this input space is fixed. But in every new function, what you call it feature, called neuron, I was relying on a new set of alphas. Somehow, at the end, I create another function. I call it z this time. Choose an alpha, and I multiply by this phi, plus another alpha, multiply by this phi, plus my alpha 0. Now this is a function on its own, and this is a function on its own. Z is actually combining both through this new vector of alpha 1, alpha 2, and 0. Well, the outcome of this, inside the box here, is a region of 0. On top here, the edges, which they were corresponding to these edges here, correspond to the 1. By just graphing x1 and x2 in 2 dimensions now, something similar to this, maybe kind of a box. Everything in this region, the outcome of this larger than 0, then belong to this class, and everything in this should be less than 0 maybe, is going to be belong to this class. But the point here, we are able to make this a transformation through this complex function. How about if I decide to use a sigmoid function? So I could do the same here by sigmoiding this. So the outcome at the end, if I draw with a sigmoid function, x1 and x2 here, perhaps looks like this. The framework of entire neural network, deep learning, or advanced AI, it's actually based on this simple concept of mathematics. I would like to demonstrate all what I've been saying here in theoretical aspect using Python, and I will show you what that looks like. Let's run this and see what we will end up with. This is the z function, and this is the k function. In other words, this is phi 1, and this is phi 2. And I am using, by the way, step function. There are 2 points. In terms of phi 1, we take one point on this region. We take another point in that region. In terms of phi 2, it turns out both points have to be classified in the same region. Well, now in the z function, when I combine both outcomes, this is exactly what we got, which is I was talking about kind of a shaping box. Now we're going to take this exact perspective and establish the principle of a neural network. So what we're going to start with actually is a kind of a real example. We have like x1 and x2. This is the simple example we've been using so far. And y, the classification problem. And we have number of 1, 2, 3, maybe n number of cases. Y could be any of these three classes. It could be class 1, 2, or 3. So in this case, what we're going to do, we're going to say transfer this y into a binarization concept. So we know now our data set and we understand. Let's take the first case. We have feature now x1 and x2 represent actually this value and this value in a vector like so. And we will say this is my input. And the size of that, it's always 1 by 2. 2 data point, that will be 2 by 2. 3 data point, that would be 3 by 2. For simplicity purpose, I'm going to just start with 1 by 2, but this one could be n. In our case here, our d is equal just to 2. What's our next step says? We're going to create these 5 functions. Remember, for simplicity purpose, maybe we can choose 4 or 5 functions for now. When I take this input of 1 by 2 and I pass it to the first 5 function, what's going to happen? This 5 function will dedicate some alpha 0 plus alpha 1 x1 plus alpha 2 x2. Right? Because we're going to like 2 input only. Same thing for the second file. We could pass all this into, as we said, the step function. Maybe we can sigmoid them. Now, the available functions that we can use here, the step function, sigmoid function, and then we had another one, ReLU function. Perhaps the ReLU function, which is very simple function actually. It says if the value is larger than 0, positive, consider it. Otherwise, if it's less than 0, then 0. So it would look like this. Well, a sigmoid, we know it should look like this. And the step function, we know it should look like this. Well, we're going to use this ReLU function, capture this, we reload each one of them. This is, by the way, layer 1. And we want actually find out how many alphas were in there. So it is obvious here we have 1, 2, 3, 4 by 2 in every one of them. So here 4, what it represents? The node number. And here again is my dimension. But from matrix multiplication, when we put all this together, that if I take this 1 by 2 input and multiply it by, if we transpose this to 2 by 4 matrix of alphas, I will draw them here actually to make it very clear, whereby the dimension of these alphas must be in tandem with the dimension of the input. The outcome of this is going to be 1 by 4. Now, let's again check the dimensionality. 1 correspond to the batch, 4. So it's going to be correspond to node number of layer 1. Now, this can be an input, just like the previous one. But this time, I'm going to construct for simplicity, like say, let's make it 3 nodes. I should also mention this. When we construct this first alpha, also we need to construct 4 alpha zeros. If you remember, each one of them had alpha zeros. Let's go ahead and look at the second layer. And to differentiate between alpha, we're going to use W here. Let's call these guys Z1, Z2, Z3, and Z4. We have 1 by 4 Z matrix. So W transpose Z plus, we're going to say W naught. Same here, we got... We're not going to do any of these activation. We're going to do something else with them. But before I tell you what we're going to do with them, what is this alpha's dimensionality? There are 3 by 4. It's 3 and 4 of these W's, whereby 3 correspond to the number of the node of layer 2, and here node number of layer 1, because this is an input which comes from the previous one. We could use our, again, linear algebra knowledge by transposing this, and it is multiplied by 1 by 4, and the outcome of this is 1 by 3, an outcome. We say we're going to do something with this, since this is the last layer, layer 2. I'm going to pass them to something called softmax, which we discussed many times before. E to that power of the value that you have divided by the sum of all other values that you have. You get a kind of a probability value. We have just constructed our neural framework. Now I have an outcome Y. We're dealing only with one case. And remember this case, I mean, the entire input here, we're dealing with this case. And this case has a Y output, and this Y output had this shape. If you remember, we binarized first. Look like this, 1 by 3. I hope that the probability here, it is as high as possible, close to 100%, because that is correspond that the actual class is. And I hope these guys as low as possible in their probability. This is the entire idea of a neural network and how to construct it. If you would have had this as the highest probability, which is wrong, of course, you guess wrong. This is an error, isn't it? Happened because of what? Because of this set of W's and alphas that we extracted. Imagine the probability of this was the highest. Maybe it was 70. The others say maybe 15. Still, we say we will guess right, but we are not so happy because we're saying 70% this is 1. Still, we are guessing it right because it's the largest. If we pass all these 3 to argmax, we return this class, but still it's not the perfect. We need this as much high as possible. Still, there's an error there. 30% we were unsure. This is a kind of error we have to account for. This is where we need to develop a new strategy to actually cope with that problem through something called back propagation. I want to remind you, with the framework of prediction principle, we say we have 3 important steps. Number 1 is to define a function. Number 2 is to define a kind of a loose function. And number 3, to take the derivative of this loose function in terms of its parameters. In this case, we have 2 set of parameters based on layer 1 and layer 2. They were actually the alphas and the W's, where alpha correspond to layer 1 and W correspond to layer 2. In layer 1, we were relying on this first alpha 2x4 and 4 biases. And then also in the second layer, we were relying on 4x3 W's and 3 W naughts. So we need to go back and take the derivative in terms of these alphas and W's. But before that, I would like to show you something quite important. Maybe there is a mechanism that we can adopt just only to quantify the margin of the error that we are doing, which we've done before, the minus log entropy. That will tell you something about how much actually are off by mistake. For example, take the log probability multiplied by y. This will be cancelled out because this is 0. This will be cancelled out as 0. And then you can tell or quantify how much error are you doing, or your model is doing good or not. Let's now talk about the loose that we're going to adopt. In my opinion, it worked very well for me. Whatever we predict, we call y hat minus the actual value. So I'm going to start with layer number 2. That's why it's called back propagation. Layer number 2, it is related to W's. So we need to go back to these W's and make adjustment on them based on the error that we have got. To do that, we need to take the derivative of this error. I want to subtract this from the actual y. So this is my first step. What is y hat? Well, y hat, it is each one of these guys here. A few of these y hat. 1 y hat, 2 y hat, 3 y hats. It looks like this. You see, this is my loose function. I just open up this guy. Now, where we're trying to take the derivative of this entire things in terms of only W1. Obviously, in this entire things, W1 is mentioned only in one place. I mean, this W1 is only here. So the other terms already cancel. I don't have to look at them at all. If you remember this entire value, it's 0.334, right? Now, what's the derivative of this in terms of W1? It's not hard to figure that out on your own. That is just only 0.334. I mean, the entire term multiplied by the coefficient of W1, which is going to be Z1. That means if I take this error and I multiply it by Z1 and the same error again by Z2, this guy, and again by Z3 and by Z4, by each one of these coefficients, I will actually get the derivative of the error in terms of W1, W2, W3, and W4. So we have just captured the error for this one column. Don't forget, very important piece of information, that Z1, Z2, Z3, and Z4, it's actually the input from the previous layer, these guys here. Same thing I could do in terms of the second, which is going to give you the W1, 2, 3, and 4 hash. Off we go. Now we have just captured the derivative of the loose function in terms of all the W's. When we do that, what we will get? We will get a new W's, but this is not enough. We need, after we do that, to update the original W fix here. To update this new W, we take the old one, which is this guy here, and subtract it from this new derivative matrix that we have constructed, which will be the same size like this. We'll multiply this by some small value, we call it learning rate. Now let's look at this W naughts. What are we going to do in there? The same, nothing special, but this time we're going to take the derivative of this in terms of W naught, the coefficient of W naught, which is 1. So it is going to be multiplied by 1. It means that the exact same vector of error. Now, the new W naught, taking the old W and subtracted from this new vector, multiplied by some learning rate. Here things get interesting more when we step back to the first layer. But the mechanism, believe me, it is exactly the same. I'm going to take again this loss function for corresponding only to the first. Don't forget the total of this is equal to 0344. Again, the derivative of this loss function, but this time in terms of the alphas and the alpha 0, which is actually this one here from the first layer. We have seen before the W's that was easy to take the derivative, but we cannot see now alpha. Why? Because alpha is encapsulated inside these Z's here. Now to open up this, move to a new page, we'll take everything from here. Our target is to take the derivative of this loss function in terms of the alphas. So the first step we want to take, it's in terms of alpha 1, then alpha 2, and so on and so forth. Now, this corresponds to the first error here. I'm going to do the same thing, correspond to the second error, which is the same exact equation actually, it should be. But this time is going to be W1 hash with the exact same term plus W2. You could see if we want to take the derivative in terms of alpha 1 only. It's not like before W1 was only mentioned in one equation. Here alpha 1 is mentioned here and here and here. So there are 3 of them are inside. And I'll show you the technique, and that is applicable then to do it in terms of alpha 2, alpha 1 hash, alpha 2 hash, and so on and so forth. Alpha 1 is only mentioned in this term, and you could see it's not mentioned anywhere else here. So all the others here are gone. We don't need them. First of all, we could see when we go inside, this W2 will be 0 and this will be 0. We have to go, we left only alpha 1 x1. So we need the coefficient of alpha 1. But don't forget there is W1. Turns out this corresponds by taking the error multiplied by the W1, which is this guy, multiplied by the coefficient of the alpha, which is x1. The second one, it's exactly the same. Now we have 3 values. Now if we take the sum of these, you will end up with one particular number. Now the same exact thing, to update alpha 1, that is nothing but taking alpha 1 old, subtract that from this total error multiplied by some learning rate. Same exact thing. Now from linear algebra perspective, if we want to make this much more practical, we cannot keep doing this for each alpha. So let's make it in a generalized form. Take the error vector 1 by 3 and we multiply by W1, W1 hash, W2 hash. This guy here, it's 4 by 3 and make it 3 by 4. What you will get 1 by 4. So just only by taking the error multiplied by the W's. And then we're going to take this and multiply it by x1 correspond to the input space. So if you take the original input, this guy here, 1 by 2, and let's multiply it with the transpose of this, the result of that will be our alpha matrix 2 by 4. Same exact thing we could do with the alpha 0. That will be the error multiplied by the W by 1. So we don't need actually this x at all. I will end up by 1 by 4 only. Of course, we take it again, subtract it from the old alpha. This is guy, and you get the new one, which is 1 by 4. This is what we want. Forward, backward, from mathematical theoretical implementation. If you capture this, if you understand this, you are able to transfer this to any code to make a neural network on a certain problem. If you get this right, you can add as many layers you want. You can increase the input space. Instead of only 2 features, you can make 100, 1,000, 1,000,000. Now, if you would have a picture, for example, like say 100 pixel by 100 pixel, if you flatten this, it become a single input like we're done here is a 1 by 2. It can be now 1 by 1,000, 1 by 100,000, 1 by 1,000,000, doesn't matter. And feed that in, and then you create as many hidden layers, whatever the names are, as you like, and then finally you can predict one of the possible outcomes. Let's take all this theoretical implementation, the math we have done, and do that in Python by creating our own neural network from scratch. Basically, I'm back on our notebook to discuss a data set which we have actually explored earlier on in previous sessions, where we have used like Naive Bayes with it, logistic regression. So you remember the dataset has 3 different classes. It looks like this, and you could see it's really complex dataset in nature, because the overlapping perspective on this dataset, it's not separable easily. But let's try actually neural network, the concept of neural network, and see how that can help. I picked 900 of them to be training and the last 100 to be testing. So this is the training dataset, looks like exactly our example in the theoretical implementation. This is X1, this is X2, and this is the label. So we got like 0, 1, and 2 labels. For simplicity, you could see here, I'm going to use only 2 neural network, just like we did in the example. I have created here a class, number of classes actually, the neural network class, another one called activation, softmax activation as well, because we have 2 different. In the first layer, we're going to use real U activation function, just if the value is positive, fix it to 1, otherwise fix it to 0. You could use also sigmoid, doesn't matter, or step function as you like. Softmax, if you remember this function, basically just simple by taking the exponential value of each input and then take the sum and then return every value divided by the sum of all of them, basically the probability. And this is going to be used for the last layer. I've created another one called the loss function. Basically, the loss function just calculate the error, y hat minus y. And it has another function called accuracy. Basically, it returned to us the total number of accuracy of prediction that we have done. And then I created a class called the propagation class. And propagation, actually, basically, it does exactly the steps backward as we have seen before. Now, let's see something, I call it the journals. You could see it's quite long here, print to print, because it's going to actually print something. Let me print actually the outcome of this journal, and then I will explain step by step what is this, which take us exactly to the steps that I've been talking about. But instead of using theoretical implementation, I'm going to actually use these outcome numbers and to show you exactly what that looks like. So this is the input. It's 1 by 2, the first 2 cases inside that training data set. This is my alphas, and these are my biases. So my alphas here are 2 by 4. You're going to take this, multiply by this plus this, you're going to get this 1 by 4, and this is the outcome of our first layer. By the way, the outcome of this multiplication has been activated. So these are after the activation. Now we have outcome of this layer, which is going to be used as an input to the second layer. And the second layer, when we made the input, we must create alphas and biases matching to this. That's why we have now 4 by 3. Because this 1 by 4, we need 4 by 3. So 3 is going to match the number of neurons in the second layer, as we said. So we get 1, 2, 3, 4, and these are 3 columns, and these are the biases, 3 of them. Now we are done. We did the multiplication, and then we did the softmax on this. And then finally, we have our y hat. And this is y hat represent actually the softmax outcome of probability. So we got the first case 33.35, 33.19, 33.44. So if we get the argmax of this, that's going to be 33.44. So we are saying this case is going to be this guy here. But is this real? This is exactly the next step we want to look at. This is my actual label. It is obviously we are done wrong here. The actual label should be this, but we are predicting this, so we have a mistake. Now, what we want to do, we want actually to get to the errors by subtracting now the loss function y minus y hat. Now we have vector that is y minus y hat. And this small minus values, you will see as a step by step we're following how much it make a difference in a while. Don't forget the actual class should be this guy. So again, to update the bias, as we said, we take the learning rate, multiply by these errors, okay? And of course, you subtract from the previous biases. That's why these shifted to be minus minus. Next, we need to update the alpha 2 as we said. So each error here, this error, we multiply by the outcome from layer 1, this vector 1 by 4. This error multiply by all of them, and then you will fill up this vector here. Second error multiply by this, you will fill this. Third error by the same vector, you will get this. So now we have 4 by 3. And then basically I take this 4 by 3, multiply by the learning error 0.01. In this case I choose. And you get this matrix, and then subtract this matrix from the alpha 2 that we have. Now we have our new alphas. We're going to do the same thing to update the first layer, biases and alphas. First, we take the error and we multiply by the old alphas, as we said, which is 4 by 3. And 3 by 1, and then you got 4 by 1, and the result is a vector will be used this for the new bias and the alphas. This is the vector of doing this. Now, what we're going to do with this vector, first we take this vector, multiply by learning rate, subtract from the bias, and then you get the new bias, 4 by 1. For the alpha of layer 1, as we done before, we take multiply by the input, and then learning rate, and here we go, we got 2 by 4. Now, my layer 1 alphas has been updated. Off we go. We want now to try this on the same case and see what's going to happen. Here, what we have got the new y hat. And I want you to watch carefully to the old and the new. Just only with one round, what had happened. Old one, if you remember, this is the largest value. Now, when we did this update, watch carefully the new update of probability what happened. Now, first of all, what we wanted, it gained 33.42. So from 33.19 to 33.42, that is a huge improvement only with one round. The other two, 33.32, it dropped down to from 33.44, it dropped down to 33.32, and also we took those down as well. So only with one round, I hope now you see by your eye, we increased this up and we took these down, both of them. And now our prediction, actually, it is right. Still not perfect, although if we do just argmax, we will win. I mean, we predict this right now, but this is not what we want. We want as much to increase the probability of this as possible. Now, that's exactly what I have done next. I'm going to use learning rate 0.01, it's fine. And now, the training data set, again, it will be 100 instead of 1. Just now we have only one case, now we will have 100. The same dimension is going to be by 2, and this is my y hat is going to match also the first 100 to see what that looks like. We're going to make iteration of 150 times. Watch carefully the result. We got accuracy of a 97%. That is a very interesting case, but this is an example, and I hope now the entire idea of neural network and how to create them on your own, actually step by step, is quite clear to you. And of course, there are some extra altercation on this framework, like using, for example, conventional neural network or RNN as well. Maybe we're going to actually look at this framework as well, and we have a chance also we can implement them to show you how the framework can be altered. That's exactly what we're going to do next. I will see you then.